I'd like to introduce our first speaker of the day, Stu O'Connor. Stu is Principal Infrastructure Engineer at Unison Computing. He's in charge of developing Unison Cloud with a team of awesome people. And Unison Cloud lets you run your Unison code on fully managed infrastructure with just a function call. And Stu is going to tell us about that now. Take it away, Stu.
All right. Thank you, Runar. I guess I'd say of all the introductions I've ever had, that is by far the most recent. But yeah, so here we are. First talk of the day. Hope everyone's excited. We're all very excited for sure. Here to talk about Unison Cloud. Like we said before, project we've been putting a lot of effort into recently, and we're super psyched that we're at the point now where we can start showing it off. And so my goal today will be to try and get you as excited as we are about Unison Cloud. All right. So, all right, why don't we dive right in and start talking about what Unison Cloud is? All right. What is it? It's a simple approach to distributed computing. Okay, but why is it? Well, because maybe distributed computing's gone wrong. And what do I mean by that? I just mean it's become really complicated and really hard. And I think that maybe we're people in a good position to ask if we should be radically rethinking some of the ways we're doing distributed computing. We as a company haven't been scared to say, step back and maybe we're doing this all wrong, or maybe it's okay if we make a language that doesn't work well with GitHub, or it doesn't exactly work well with LSP, the language server projects, because we think storing source code and files on your disk is just outdated way of thinking. And so we want to start off by, talking about how software development used to be just like a lot simpler. You just write a program and then run a program. Let's go back to how things worked on my first computer, a TRS-80, back in 1982 or 1983 or whatever it was. So here you go. You would just fire up basic A, you'd write some code, and then you'd hit F2 to run your code. How could it be any easier than that? Or I don't know. I guess you could hit F6 for Tron first. That's cool. But, and actually, if you look carefully at this basic or know much about basic, you probably don't want to run this program. But I don't know. Things were simple. You hit F2 and you run. But of course, knew this wasn't always going to be this simple, and the world was changing, right? Because now your computer's online. But that's cool. But hey, software development still can be pretty simple. Here we are running some CGI bins in Perl, and look, people are signing up to my guest book, and this is still fun. But, software is about to become the extreme, and it's understandable because now, everyone's online, right? And everything is online. And that's going to change the way we write software. And it's going to become a lot more complicated, right? And then our data is going to get bigger, and we're going to have to change the way we think about how we deploy software so we can process all that data. Just not only is all this getting more complicated, but the way we deploy software is getting more complicated, right? Remember we used to upload jars with some classes in them, and then we had web applications, and we were deploying WAR files with WAR XML, yay! And then we decided enterprise Java beans or whatever the heck Java server faces were, and we had ear files, and this accelerated, and things are very fast, still becoming more complicated, right? I mean, this is like an old snapshot of AWS from years and years ago, and now there's 10 times as much of this stuff out there, right? So let's talk about some other ways people are deploying software now and how many ways it goes wrong, right? Maybe this is how you're distributing software today. You build a Docker container, you push it up to your company's repo, then I don't know, maybe you ask Kubernetes, can you run my Docker container for me? Run my thing 23. And you're like, yep, that's the right version. And no one wrote over my version. And yeah, fingers crossed, we're all rooting for you. What could possibly go wrong? Or maybe you're working with Spark, right? You make a big fat jar, it has all your dependencies in it. And then you try to get the Spark cluster to run your job for you. And I hope you realize that the DevOps team finally got around to upgrading your Spark cluster. So now you don't have the right version of Spark, and things are not going to go very well. And the dependency problems with Spark, they never go away, right? So like Spark's going to be like, hey, you got the right version of Akka on there, and you're going to be like, I don't even know what Akka is, and it's just like, yeah, fingers crossed, Godspeed. Here's one I'm sure a lot of you have hit, right? Suddenly SPT is like, your build is broken now for some esoteric reason, and you're like, oh my God, there was only one person in our company that understood SPT, and now he's gone. So you're like going to Stack Overflow, and you're trying to figure out how to fix SPT, and the SPT community is like, it's no big deal. SPT is just like a big applicative builder under the hood, and once you get that, you're golden, and you're just like, I want to do machine learning. Now I'm like having to figure out the SPT guy, and the next thing you know, you are the SPT guy, and you're just like, oh my God, I hate my life. I just want to work on my software, right? Okay, but we're going to be done with all that now. My goal is going to be convince you that, Unison Cloud is going to make all that stuff obsolete. Like we're going to go back to, or we're going to at least try to go back to that happy place we were in before. We just write a program and run a program, and that's it. So I think Unison Cloud is going to get to be feeling more like that. So let's talk about what it might look like to write software for Unison Cloud. It all starts with this remote ability. And the most fundamental thing you can do with remote is fork. And what does this do? It starts a possibly remote computation that will produce some value of some arbitrary type A at some point in the future. And so that's a lot right now. So we're looking at this type signature of fork. Let's take it apart and see what it says. All right, so we see there's two arrows, so it takes two function arguments. One argument is the thing we want to run. And the first argument is where we want to run it. The return type is going to be a value of the type task A. This is like a location where a result's going to eventually go. This is something you might be familiar with from other languages or libraries as a future. And so we want to get the value of our future. We can await the task, which should produce an A. It might fail, which is why calling it requires the remote ability here, because it might need to call remote.fail to fail the computation. All right, let's take a closer look at this argument, the computation we want to run. People that are less familiar with Unison syntax might not be as familiar with what this type says. So let's break it down. I mean, especially, we're here first talk of the day and we're just getting warmed up, right? All right. So the first thing we want to look at is that single quote at the beginning. That's Unison shorthand for a thunk, or a delayed computation. It's just shorthand for a function that takes a unit as input. This is the totally equivalent syntax. So like it's a computation that's not running yet. It just needs a little nudge of you handing it that unit to get things going. The other thing that people might not be used to is the bit inside the braces there, which is the list of abilities needed when you run the function. So this says that when you do pass that unit argument to the function in order to start the computation, it has to be done in an environment that has access to remote ability, and it has to be run with inside an exception handler. The G parameter is a placeholder for anything else your computation might need when it runs. And we'll talk more about that later. But what this signature does tell us is that we know for sure we're going to need at least remote and an exception handler. All right. So let's go back to that location argument from our fork function. Right? What is that argument? A location is a logical location of a running node inside your cluster where we could want to run a computation. All right. But how do you get your hands on a location? There's a couple ways. First is you can always get a handle on the current location by calling here. And then there's also another special value called current region, which refers to any node in the same region as me. And then given those two, we have two other functions that help us discover even more locations. We have a near function, which we use to find a location that's logically near another location that we already have. And what does near mean? Well, today near means here. But we hope in the future we can be a little bit smart about that. Maybe we could say, I know you want to be running here, but here's a little full or a little busy right now. So we're going to get somewhere nearby. And then just like near, we have far, which does a similar thing. It says, I want you to run somewhere far from here. Okay, but how far is far? What does that mean? Could it be anywhere? Well, I want you to notice that, these two near and far functions, they take two locations as input in order to produce one. So if we look at how they're actually used, it should hopefully make a little more sense. So here we're getting two new locations, near location, far location. The first one, remote.near, current region here. This says, find me a location in the current region that's near to here. The second one similarly says, find me a location in the current region, which is far from here. And like I said, in general, right now, near is going to mean here and far is going to mean anywhere but here. But at least we have this bounding box, so we can say it, but it has to be in the same region, right? And this is something that we think has some quite potential too, because we hope that soon we're going to be up in multiple regions. Maybe you could say, find me a location that's inside US East 1, or find me a location that's inside US West 2. And this is something I think that has a lot of exciting potential, because cross-region computing is something that in the past has been kind of really difficult, and maybe we're going to find a better way, make it simpler. You might notice there's these G parameters outside the location, which I've sort of been ignoring. So let's talk about those. So this G refers to abilities that you need to have as part of the location that's returned to you. So these are abilities we're going to need in order to execute our code. So the way this works is when we call near or far, we can specify that we need the location to come back and have some abilities for us in order to execute our code. But, all right, what are the possible abilities? All right. So we have a few, and we're hoping we're going to bring a lot more. But what I'll do for now is I'll talk about the abilities that we've got to start with, and later we'll talk about the potential for more abilities. So here's one. We have a channels ability, and this is one that'll be available at every location. So if you ask for a location with channels, any location will work. And channels are kind of like message queues, right? So, and what I have here is a simplified version of the channel ability. The real ability has like a bunch more possible operations, but what I wanted to do is to pare it down to something simple so you can get an idea of what channels is and not overwhelm you, right? So this shows you basically, gives you an idea of what you can do with channels. So you can create channels, you can send messages to channels, and you can receive messages from channels. You can choose if you want to receive messages in a synchronous or an asynchronous way. And you can see this is, a lot of potential here for things you could build out of this. You could build something that looks like an actor system. Maybe if we start rethinking how we're going to do services, this is a way that you could send messages to a service with instructions on how to get a response back. But we think of, these first few abilities and the remote ability, we really think of as a low level something that we're going to be able to build lots of other cool stuff on top of. So this channel's nice little simple interface, but lots of potential. We also have a scratch ability, and that's again one that's going to be for now available at every single location. And again, this is a slightly simplified version for demonstration purposes. So just want to give you an idea what it feels like. But what is Scratch? Scratch is non-durable storage. You can use temporary storage for values that you might need to store for a short amount of time, maybe because you're going to store a value because you have more than one computation read from the same value, or maybe you're going to cache a value that you might want to refetch later instead of recomputing. And again, like channels, this is like a very low level interface that we're excited about all the things we're going to build out of it. Another ability we recently added is HTTP. This is, what you'd expect. It's a way to do HTTP gets. It's a way to do HTTP posts. Of course, we handle deletes and patches and puts and all that stuff under the hood, but I'm just showing you the basics to get a feel for it. And it does, acts roughly as you expect. You give it a URL, you get a response. You give it a URL and a body, and you can post and get a response. But this one's a little bit curious if you're paying attention, because you might say, no, why would you need an HTTP ability? Like, I've already seen you have an HTTP library. Why can't I just make HTTP calls? But, think about what the value proposition is here. The value proposition is that we're going to run a cloud, and we're going to let you upload your program to our cloud, and we'll run it for you, right? But we can't just let you, run any code you want, right? We're not going to let you do arbitrary I/O. Like, for example, we're not going to let you run around and see what's on our file systems, and we're not going to let you maybe make arbitrary network connections and stuff like that. And interestingly, because of the way Unison is structured and the way it works, it's actually easy for us to do. We can scan your program before we run it and look around and see if we see any of the hashes that refer to any of the I/O build-ins, and just say, I'm not running that, because I could see for sure you're calling, IO.openFile. So this HTTP ability is a way for us to say, all right, you can't do any I/O, but you can do this stuff. You can fetch some web pages and stuff like that, right? All right. So moving on, let's talk about how we might write software for remote, right? So here's a little program. It calculates a very important answer. It calculates the number 42. So let's look at this and see how this works. Well, so you look at the type signature, you see that what we've got is a delayed computation. There's a little tick mark there next to remote. So it's a delayed computation that needs the remote ability to produce a natural number. And how does that do that? Well, it creates two tasks. It creates a 20 task and a 22 task. And it decides where it's going to run those by picking random locations using our far command, right? It says far region here. So that's going to pick any random location that's hopefully not here. And then we see it's got a very simple little computation. 20 is 10 plus 10, and 22 is 10 plus 12. So we fork both of those tasks. They're off and running on different nodes. And then what we can do is call our wait function and say, I'll wait for those results to come back and add the two results. Right. This is, not too bad, right? And it's pretty cool when you think about what's going on here. We have 3 computers all collaborating on doing one computation, right? And we're moving functions across the wire, because that's something, Unison knows how to do. We know how to serialize anything, right? And we're doing this network computation, but you don't see us talking about the network too much, right? And we don't have to talk about serialization. The values are all going to be magically transported for us. And this is something that's, special to Unison. Our ability to serialize closures and functions like this is, one of the crazy things that we decided to do that's going to make a lot of this stuff, possible and easy. So there are, of course, a few foot guns there, right? You can't necessarily send an open file across the network and expect you're going to still be reading from the file when it gets to the other side. Or you couldn't hand an open network connection, or we can't close over an MVAR or a TVAR, or these kinds of things. But other than that, Unison's very helpful as far as getting their values around. And like I said, we don't have to talk about the networking. We don't have to talk about the serialization. What we're going to end up talking about more is our problem domain, the thing that we actually want to spend our energy on. All right. So how are we able to get all this to work? I think it's really interesting to, talk about, again, why Unison is special and how we're able to make this even happen. So here's a simplified version of our 42 program. That's just adding 2 numbers, right? But it's important to remember that this is not how Unison stores your code or thinks about your code, right? Because we don't store your source code. We turn everything into an AST, and we store the AST, all right? So here's how your program would be represented as a tree. But the other important thing about Unison is remember that it's content address, right? So Unison hashes all the parts of the tree. It generates a hash for the entire tree and refers to the function now on from then on as your hash. So here I am showing a 2-byte hashes just for brevity. Inside, of course, we're using SHA-512. What this means is that if you have the hash of a function in a Unison code base, you can go look up the definition of a function. And so this is what can make it very easy for us to distribute your software for you. let's look at how we might do that. So in Unison Cloud, we want to run a function. We just simply say, hey, Cloud, can you run this computation for me? And we just have to refer to the computation by its hash. The Cloud maybe hasn't seen this hash before. And so it can ask us, can you send me the tree for that hash? And we can respond and say, yeah, sure. 3DF7 is the subtree 9046 added to the subtree C63E, right? And for our simple example, we're going to assume the Cloud has heard of 22 before, and the Cloud has heard of 20 before. And so it's got everything it needs now to run our program. But with a larger program, this might take a couple back and forths where it's going to say, okay, now I actually need you to tell me what 9046 is too, if maybe that was a whole other AST. But we know that by recursively asking over and over, we can get your whole program up to the node that you're talking to, the one node you're talking to. But of course, Unison Cloud is going to be made up of many nodes. It's going to be a peer-to-peer network that, collaboratively works to execute your computation. So how's that going to look? So we're going to start by picking any random node in the cloud. And this is going to largely go as it did before. We're going to have a conversation with that node, and we're going to make sure that it knows everything about our application, and it's going to be ready to go. And then what is it going to do? In this case, it's going to go pick 2 random other nodes to help out in this computation. And it's going to have a similar conversation with those nodes where it can make sure that the nodes which are going to execute parts of your program have the parts of your program it needs. And this is something I think is like super cool. Like, we don't have to worry about how we get the software to the nodes. We know we can do it. And it's all automated. But, it's kind of a shift in the paradigm in the way that we're doing things in our cloud, right? Like, instead of shuffling data all over our cloud and moving it from one microservice to another, or maybe moving it into Kafka to move back to a microservice, which is going to put it back into Kafka, which is going to come back to another microservice. And we're shuffling the data all around. But, maybe that's not the smartest way to do things, right? Here, what we're showing is we can instead move the code to the data, so that the code just goes to where the data already are. And that's because, these days, remember, our data is big, and the data has gotten a lot bigger than the code. So let's stop shoveling the data all around inside of Kafka, outside of Kafka, back into Hadoop, back out of Hadoop. And let's just see if we can move the code to the data. All right. So, like I said before, a lot of these things that we're building on now, like the, forking tasks, awaiting tasks, scratch space, channels, these are all building blocks that we're excited that we're going to build bigger and better and more interesting distributed libraries on top of. So spend a little bit of time talking about one of those that we've already worked on, which is this Seek. And this is one that if you go to our blog, Paul wrote a great blog post introducing this called I think it was Spark-like data structures in 100 lines of code. But all right, let's talk about what a Seek is. It's a distributed collection that's built on top of remote, like I said, and it's also built on top of Scratch. And if you're familiar with Spark, you might think of this as being a lot like an RDD. It's like a distributed list, maybe, that has parts of the list on different nodes around the cluster. But all in all, it makes up a list of lots of things spread across the cluster. So I listed here some of the things you can do with a Seek. The first 2 should be obvious. And we've got map and reduce, right? And this is the thing that makes it RDD-like, maybe. The next 2 are the exciting ones. Memo and memo reduce. That's where we're using Scratch space. So what those memo functions allow us to do is to take a computation that we're working on and just say, hey, let's do a checkpoint and just want you to save all that data to some temporary spot. And then we'll keep going. And the idea here is that then if we ever need to go back and repeat this, we've already got a part of our computation is already stored away, and we can skip that bit. So if we have to rerun a computation, we might not have to recalculate everything. And think about it, this is something that happens to people running, say, Spark all the time. You've got your Spark job that's been running for hours and hours, and you realize, oops, I made a mistake in like the final reduce. I'm going to have to redo that, which means, reprocessing everything we've done so far. But here this is going to save us. Like this is going to say like, hold on, we already know these values, and Unison again is very uniquely positioned to be able to do this, because we're able to say things like, what's the hash of this function? And later we could say, has anyone ever calculated what this function returns? Right? Because we're really good at it saying, okay, if you know about this hash, I know what the answer is already. Right? All right. So what I want to do now is to kind of show off something that's a little bit, more of a real piece of software, not like calculating 42 or some Fibonacci numbers or something like that. So, because I want to show off that, we're starting to do real stuff with Unison. It's not just a toy anymore, right? So me and one of my teammates, Cody, we decided to do some real work on a real data set. See if we can do some real machine learning or something like that. So this is the data set we got from Kaggle, which is a great place for learning machine learning and related fields like that. They got a bunch of cool problems that you can work through to learn about that kind of stuff. But they also have a lot of cool data sets that you can just play with. So this is one that we picked. It's got 700 or so JSON files about asteroids which are in orbit around Earth, and they with ones that have recordings about when they made close flybys in the past. So we decided to see if we could crunch this data set and just do something that's more than just, like I said, making Fibonacci's or adding ones together, counting words. So here we're going to go through all the asteroid data and see if we can find the closest ever flyby of one of these asteroids. All right, so let's look at some Unison code and see what this looks like. Right? So we start off, we made some simple data types just to store the data that we're interested in collecting. So we got asteroids and their names, and we've got all these list of previous times they had close approach to Earth and how close they got, how fast they were going. All right. So now what we did is we uploaded all 700 and whatever files at the S3 and into one of our S3 buckets. And so, here's the code which uses our HTTP ability we talked about before to try and download a file from an S3 bucket. And my goal here is not to try and get everyone to understand every line of this code. But, it should be pretty easily understandable. You should be able to see what's going on here. Like I said before, we're declaring our HTTP ability, we're constructing a URL, we're making a GET request, we're turning that into a response, and we check to see if it worked. And if it did, we interpret the body as UTF-8 text. Cool. All right, what are we going to do with this text? It's JSON, and we got JSON libraries. Right? So this is a JSON library. This is showing how we're using a JSON library that, again, Cody and I wrote. We modeled it. It's very much inspired by Circe or Argonaut from the Scala land, which is the ones that we're most familiar with. And I didn't show all of the parsing data. I did show just the asteroids. I'm not showing the flybys and the dates. Again, I just want to get you a little taste and show you that hey, we're doing real stuff. All right. So we parsed all JSON. We decided our goal was to go and find the closest asteroid, right? So we're going to need a little reduce function that can compare two asteroids. Here you go. This is going to go through and look at all the flybys, find out which the closest flyby is for a given asteroid, and then compare the two asteroids just by comparing floats. That's just simple enough, right? So at this point, we're kind of ready to put our job together, right? So let's put it all together. So here it is. This is our program. This is us using Seek to find the closest flyby. Right? And it's easy to read, right? What are we doing? We're taking all the files. Then we're asking Seek to chunk those up in bunches of 100. So we're going to take batches of 100 of files and we're spread them all around the cluster. Okay. And then in parallel, we start to get them all going, and they're all going to start fetching that stuff from S3. And then we parse the JSON. Then we're going to call our cool memo function. And then we're ready to reduce. So here's the really cool part, right? Let's say we decided, you know what? Closest is not as interesting as fastest. So we're going to change our computation. that I don't want to reduce and find the closest asteroid. I want to reduce and find the fastest asteroid. And that's simple, right? We're just changing our one reduce call from closest to fastest. Easy, right? But here's the really cool thing, right? When we go to run this computation again, it's going to be a lot faster, right? And there's two reasons for that, right? So one thing you'll notice, like I said before, this program is very similar to our previous program, right? So remember when we're doing that conversation with Unison Cloud and we're saying, hey, can you run this hash? And it's going to say, what is that? Well, now Unison's already going to know what all file names are. It's going to already know how to turn asteroids from JSON into asteroids. Right? So when we go to say, can you run my program? All we're going to need to send it is just the tree for asteroid.fastest, our new function. It already knows everything else. Right? But then, of course, when we go to run the computation again, we aren't going to have to download all the files again. We're not going to have to parse all to JSON again because our super cool speak.memo function stored all that stuff in our Scratch ability. And so now when we get to start our computation, we get to start right from the reduced start, which again, super cool. I think this is something that could save a lot of computation time. All right. So, another thing we never talked about this whole time is we never talked about, like, how do you actually run something in Unison Cloud, right? All right. I got two ways here, right? And you do these right from inside UCM, right from inside the thing where you're managing your code, right? First one, remote.pure.run. This is a way to run a remote computation, but run it all locally. And this is a great thing for when you're still developing your software. When you run with pure.run, everything happens locally. So like calls to near or calls to far, all just going to return here, because that's the only place we know about. Once your software is good to go, you get to run it in Unison Cloud and use our second way, right? Remote.cloud.run. This one is going to do all the thing we talk about. It's going to send your computation up to the cloud, close to a cloud node, make sure the cloud node has your whole program, and it's going to start running it, and we'll wait for an answer to get back. Right? How simple is that? Right? It's pretty easy. Is easy hitting F2? Maybe not, but we're getting pretty close, right? This is going to be fun again, and it's going to be easy. All right, so where do we go from here? Like I said before, we're just getting started, and we're super excited. The things we're producing now are the low-level building blocks that we're going to build on. So, for example, the way we're able to combine the remote and the Scratch in order to make the speak interface. We're excited about other things we're going to do like that. Like we think we can take the channels of interface along with the Scratch interface and make a distributed hash table, right? And we're planning on not only having Scratch space, but we're going to add some persistent storage. So something that won't necessarily get, pushed out. Something you can guarantee on being there. Our most recent hire, Travis, he comes with a whole ton of Postgres expertise, and he and Runar are off and running and getting us a Postgres library. And I think that's going to really enable a lot of people to do more real work inside Unison. And another, exciting development that's going on with Unison that we're going to talk about later today is that Dan Dole, our compiler engineer, is working hard on getting us to native compilation, which is super exciting to me, right? And it's exciting to me for a couple of reasons. One is that, first of all, things are going to start going way faster, right? Like hundreds of times faster, I think. But more exciting to me is that that's going to open up possibilities for us to be able to do FFIs by linking to C libraries, right? And I think that's what's going to get us to being able to have a GPU library. And that's super interesting. Think about being able to say, hey, Unison, I want you to launch this computation for me, but do it on a machine that's got GPUs so I can use CUDA to make really fast vector math, right? That could be like a game changer. And so, just the way that we're rethinking how we're doing this distributed thing, we, like I kind of hinted at before, we want to maybe rethink about how we do services. Maybe we can, think of a better paradigm instead of a jumble of microservices that might not be agreeing on their version on, stuff. So what else is next? Soon, we're getting ready to launch the Unison Cloud free tier. which I think will be exciting. The idea here is we want people to be able to start playing with remote and channels and Scratch and Seek and all that good stuff as soon as possible, right? So the idea here is you'll just be able to fire up Unison, authenticate through GitHub auth and remote.cloud.run, and send us your computations, and we'll run them for you. So yeah, hopefully that's going to be coming soon. The idea will not be that we are going to run all your computations, but we want to let you have some limited playing time and see if we can help get you, like I said, as excited as we are about all this stuff. So with that, that's all I got. And like I said at the top, my goal was to try and get you as excited as we are, to rethink how we're doing distributed software and make it more fun and less, I don't know, Docker and Spark and stuff. So, but please, I love to talk about the stuff. So please come find me. I'm always on our Slack, and I'm always ready to geek out. So don't be shy. But yeah.
Thank you, Stu.